Next presentation is entitled Artificial Markers Recognition for ERC Competition and Their Possible Use on Mars. Please help me to welcome Michał Hałoń.
So hello, my name is Michał Hałoń and I'm a member of SK Robotics project in Student Space Association at Warsaw University of Technology in Poland. And today I'm going to talk about artificial markers recognition for European Rover Challenge competition and their possible use on Mars. So I will start with mentioning about the fiducial markers definition, what they are. I will show a few examples of them. Next, I will present current use of markers on Mars in the example of Curiosity rover. And then I will present some ideas of the possible use of these markers on Mars in the future. I will briefly describe the European Rover Challenge competition and then present my algorithm for detection and recognition of ERC landmarks, how it works, how it performs, and I will present comparison of my algorithm with the already existing publicly available algorithm. And finally, I will summarize my presentation. So, fiducial markers are objects placed in the field of view of an imaging systems that are visible in the image and can be used as a point of reference or a measure. So, for example, thanks to them, we are able to calculate the position and orientation of camera relative to the markers on objects that are labeled with such markers, and vice versa. And what is more, we are able to compute approximate distance between camera and such markers. And here I presented a few markers. A few of them, like QR code, are designed for carrying information like text or website link, but most of them, like R-tag, April tag, chroma tag, are real fiducial markers designed, as I said, for being a point of reference or a measure, and every single marker has its own ID. When you look at the Curiosity photograph, it's hard to find any of markers on it, but when we look closer, when we zoom it in a specific component, we can see some of them. And these fiducial markers on Curiosity rover can be used, for example, for camera calibration or other devices like robotic arm. There is more than one kind of markers on Curiosity rover. For example, this is an augmented reality marker. And as far as I know, there is also a marker that has a shape of rover. And these are markers that we aim for color calibration. So as we could see, the current and present use of markers on Mars rovers is for camera calibration or calibration of other devices, for example, robotic arm. But what if in the future Mars was full of autonomous Mars rovers? Would there be any other usage application of such markers more than the ones that I already mentioned? I think that such markers could be used for autonomous navigation. For example, on Mars bases where autonomous rovers could approach hubs, could just drive on specific routes and avoid certain obstacles. The second idea is that autonomous rovers could operate on controlling panels, like the panel I presented here. Such panels could be labeled with fiducial markers to help calculate the orientation and position of rover robotic arm in relation to the control panel. And what is more, each switch could be labeled also with fiducial markers to enable teleoperator or autonomous rover to manipulating on them. And the third idea is that every tool, cache, or sample could be labeled with such markers to enable easy detection and recognition of such an objects and to calculate the position and orientation relative to these objects. And students, teams participating in European Rover Challenge competition have already opportunity to simulate such a future Mars mission. For example, maintenance task is a task where rover has to operate on control panel that I presented here, and this panel is labeled with such markers. And what is more, during traverse task, a rover has to autonomously achieve 5 checkpoints, and the only information allowed to be displayed on operator console is the position and orientation of the rover, and such data like position and orientation can be calculated by navigation using artificial landmarks like the ones presented here, which are cuboids with its IDs encoded on every sidewall. And in our team, I was responsible for developing an algorithm for detecting and recognition of such an artificial landmark. So I started with calculating how long should my algorithm work to enable proper localization and navigation of a rover on Mars yard, and here are the results on the map. I assumed that to properly navigate on the Mars yard, rover could detect at least 3 different landmarks at the same time. And when I thresholded this value to either above or below the value of 11 meters, it turned out that if rover's algorithm of detecting such markers could detect them at least from the distance of 11 meters, it could navigate at the major part of the map. Next step was choosing the right markers to detect, because such a landmark has a it has its own ID, for example 1 or 50, but it's encoded in 3 ways. First is just a real number above. Second are blue dots on a green rectangle, and the third way are the artificial fiducial markers called artifacts. And for our purposes, I choose the third option, the artifacts, as I believe that they are the most robust and efficient way to detect such landmarks. And when we looked at all the landmarks, the artifacts that we had to detect and recognize on this competition, beside the one in the lower right corner, which was used for other purposes, we can notice that they all have something in common. First, they all have the same pattern in the first 3 rows. And these artifacts are just black squares with its ID encoded in a pattern that consists of smaller black and white squares. And as I thought, first they all have the same pattern in the first 3 rows. And secondly, they all have just 6 white squares in the two rows below. And that this observation was the main basis of my own algorithm of detecting such markers, which steps are as follows. First, in the quadrangle detection phase, my algorithm looks for edges on the picture, and taking into account not only the edge but also its direction, it classifies them into four different edges depending on their direction. And from these four types of edges, it looks for quadrangle, which is a possible black square of artwork. During the second phase, the marker recognition phase, the possible marker is being transformed to its basic position, and then its edges are cut off. Next, such an image is binarized to put a grid on it, and inside this grid, at every cell, the algorithm calculates the average brightness of this cell, and for every possible artwork, algorithm in first three rows, where every artwork has the same pattern, looks whether in the expected black squares there is exactly lower average brightness of it, and if it is so, then it looks for the 6 brightest white squares in the 2 bottom rows, because it's looking for these 6 white squares. And when it creates such a pattern, it matches the pattern of possible artwork with already existing patterns of real markers, and when it succeeds to match it, it mark it on the image or just give some data about marker detection, and if it does not succeed, it just discards a potential quadrangle as not belonging to the markers library dictionary. And many of methods for detecting and recognition of such markers use binarization, just by binarization to extract white and black squares. And during my work, I noticed that at some conditions, especially when the markers are very distant from the camera and the resolution is very low, such a black squares are not visible, like here. And this is the other example. We can see that we can distinguish the black and white squares inside this white part. And my algorithm of calculating average brightness seems to overcome this problem to some extent, and just to work better. In order to measure the performance of my algorithm, I prepared a special test stand, which consists of 3 cameras and, of course, landmarks. And every landmark was photographed at 3 different angles. The first perpendicular to the camera, and then rotated by 45 degrees to the left and to the right. I've taken hundreds of such images, and with decreasing distance of markers, of landmarks from the camera, in range from a few meters up to 20 meters. And here we can see how the quality of such artworks decreases with increasing distance, but for lower resolution images, this quality drop is visible even bigger. And here are the results of my test. When we look into results of lower resolution cameras, which is HP and Logitech, and we look at distance of 11 meters, I already mentioned about this distance, we can see that my algorithm detected only about 30% of visible artifacts markers on the image. That's definitely not enough for creating a robust and efficient algorithm for competition. But when we look at the higher resolution results, we can see that up to the distance of 12 meters, my algorithm detected all visible markers, and with the distance of 20 meters, the accuracy is still better than the accuracy of at 11 meters for lower resolution images. Here are some example photos of how my algorithm works. And it turned out that it works even when in various conditions, even when the sun is visible in the image at the same time with landmarks. And it also works when the markers are variously oriented, relating to the camera. I tested my algorithm also on photographs coming from previous European Rover Challenge editions, and here you can see that on super high resolution image, algorithm detected a marker that number one that was a distance to which was about 26 meters, but this was the super high resolution image. And during European Rover Challenge 2018, our rover called Sirius has had to manipulate on control panel, which was labeled on such artifact markers, and from our onboard cameras, we were able to detect these markers, which could help us to orientate our rover relative to this control panel. And I decided to compare my algorithm to the already existing algorithm publicly available called Aruco. This algorithm is implemented in OpenCV and is based mainly on the binarization by Otsu method to extract white and black squares. And it is not designed for artifacts we use at ERC competition, but for markers called Aruco. But it is also possible to detect markers with use of this algorithm that are of different kinds. For example, April tags and other. And to do this comparison, I used a formerly prepared image dataset that I have already presented. I've already prepared the programs to automatically optimize parameters of both our algorithms, my and Aruco algorithm. And finally, I determined the accuracy and the error rates of both algorithms. And I used two algorithms, but there were a few models of these algorithms. For example, original Aruco is an Aruco algorithm without parameters optimization. So just original Aruco, and the best Aruco stands for Aruco algorithm with parameters optimization. Aruco zero error is Aruco algorithm with parameters optimization, but with requirement of zero error rate. So this algorithm couldn't make mistakes. For example, couldn't find markers where there wasn't any, or couldn't mistake the number of markers. And MSC zero error is my master of science algorithm with parameters optimization, and just plain MSC is my algorithm, but the previous version without parameters optimization. So on this chart, on the horizontal axis there is distance in meters, distance from markers to the camera, and in vertical axis there is accuracy at specific distance. And for original Aruco without parameters optimization, we can see that it couldn't detect any markers of higher distance than 40 meters. But when I automatically optimized its parameters, it did much better. It could even detect markers at the distance of 20 meters. But with this requirement of zero error rate, that this algorithm couldn't make any mistakes, the accuracy dropped a bit. And here in the red line, there is my Master of Science algorithm with zero error rate. It works better than Aruco algorithm in middle distances and definitely in the distance of 20 meters. And this is my original MSC algorithm. We can see that without parameters optimization, its accuracy performance watch was quite worse. So to sum up, my algorithm turned out to be the best at this image dataset after automatic parameters optimization. The overall accuracy was about 85% with zero errors, but computing time was quite bigger for my algorithm than for Aruco, but I think that these values are still acceptable for such a systems. And I think that my algorithm will work better because I did some observation of characteristic of markers I detected. And I think that I could try to create a new algorithm and new markers library that are based on this observation that there are some patterns existing in every marker of the library, and that there's in some specified rows there is a specified number of white or black squares. And to sum up my presentation, in my opinion, systems based on artificial markers could play a significant role in future missions, especially those including an autonomous Mars rover. So I think it is worth to develop such an algorithms that are specially designed for autonomous traversing on Mars, designed for operating on panel or on control panel, or just for grasping, manipulating on objects from the ground. So thank you. Any questions? Yes.
Perhaps a very simple question, but does this presuppose that that the staff has gone out and put the markers physically in the terrain? Have people put the physical pole with the marker sign on it, like we saw in your demonstration?
Yes, that's why I mentioned that such an algorithm would be useful in Mars bases, where autonomous rover could drive through from hub to hub, for example, and there people could put first such landmarks.
So it would become a very routine task.
Yes.
Thank you.
Okay, so it's less than a question, more than what I want to say about that. As AI specialist, at least that's what it says on my resume. Since you are still using OpenCV, you might as well write a functional network of that and combine both methods of recognition, or three methods of recognition, into a network, and then let the network itself choose which method it uses for that particular reason. That would make your recognition even better. And if you program that on OpenGL, so on graphics cards, that would make your algorithm run in less than a second. So you would be even better than that.
Great idea. I implemented my algorithm actually in MATLAB software, but it could be.
Well, since MATLAB runs on C, and transcription from C to GLSL is not that hard.
Yes, exactly.
Sorry.
Okay.
Two kind of quick ones. How big are those physical markers, and how long did it take you to program your algorithm?
So these markers are squares of about 20 centimeters. So 20 centimeters by 20 centimeters. And the second question?
How long did it take you to program your algorithm, and was it just you doing the programming, or did you have contributors for programming?
So I implemented this algorithm myself, and it took me 2 months to create about. Okay.
I noticed that the top line was always an orientation index. Will it still recognize the markers if they're rotated or turned upside down?
Yes. The algorithm just rotates every possible marker by 90 degrees 3 times. So it's okay to rotate it in every direction. So thank you.
Thank you, Michał.